The purpose of this lab is to determine the magnetic dipole and magnetic dipole field produced by a bar magnet using a magnetometer. The magnetic fields will be parallel, perpendicular, and off-axis to the magnet. To do this, we will need the Biot-Savart law to calculate the field. We will also need the distance dependence equation for an electric field. We were successful in calculating both the magnet dipole and the magnetic field. The system for this experiment will include the bar magnet and the magnetometer in the phone. All measurements will be taken at rest. To conduct the experiment, we need to compensate for Earth's magnetic field, so we orient the magnetometer so that the x component was almost zero. We then measured the distance required to observe a few different magnetic field values. Some were on axis, others were off axis. Here are the results from these measurements. We found that when close to the magnet, the x component increases, but when the magnet is moved away, it goes towards zero. From that, we're able to get the distance dependence of this magnet, which is the slope of the graph in the previous slide. We can also find the k constant from this equation. Mu can be found by setting the distance-dependent equation for a magnet field equal to the perpendicular equation for a magnetic dipole. With this information, we can create some Python code to simulate this experiment. First, we need to input mu, which we calculated experimentally. Next, we need to create a function using the Biot-Savart law to calculate the magnetic field at a given location. We then create a number of vectors that are on axis and perpendicular to the direction of the magnet's axis. We can also create a few vectors for an observation location at 45 degrees from the axis of the magnet, and use the function that we created to calculate the magnetic field for these locations. We'll also create arrows to represent these fields. Here is the graphical output from the Python code. The model output and the experimental magnetic field at the same location were much different. This could be because there were electronics in the room when we conducted the experiment. The electronics could interfere with the readings on the magnetometer. The orientation of the magnetometer may have been off when we took some measurements, so Earth's magnetic field might have had more of an effect than we thought. If we did not compensate for Earth's magnetic field, then we would find a much larger mu since Earth's magnetic field would contribute to the field more. Likewise, if we stuck two magnets together, we would expect the value of mu to be much greater since it would produce a much stronger magnetic field. That's about it. See ya.